PLCs have become extremely powerful, and nowadays one does not have to hesitate to make use of a PID controller. In fact, in the old days, you would be limited quite severely by the amount of controllers that you could go and use in your circuits. And nowadays, we've got a lot more flexibility and freedom because the devices have become a lot more powerful. Now, for most of us, we're going to work with a feedback loop, and that means that we're going to go to the process, and from the process, we will measure whatever signal is going to be coming along. And that measurement is, of course, going to be done by means of our instrument that we would have out in the field. That signal is then going to be sent to the controller, and that signal is known as the PV, or the process variable. That gets taken up into the controller, and inside the controller it's usually going to be compared to the set point, and based on the algorithm inside the controller, it will calculate what the output is going to be. That output will go to your final control element, which for many of us is going to be a control valve or a variable speed drive, and that in turn is going to have an influence on your process. The controller works on the error, and the error is going to be the difference between the process variable as well as the set point. And then you can have a direct acting controller, or you can have a reverse acting controller. And please go back to the section on practical process control, where you will see all of this explained in more depth. A couple of decades ago, it would have been a lot more difficult to program a PID controller. In fact, it would have taken pages and pages of code to get to this point. Nowadays, all that you and I need to go and do is grab the correct block, and you literally are going to go and drag that block into your PLC program, and it will do all of the work for you. You can tell it what memory location to go and read for your process variable. We can go and give it a set point, and that set point can be changed by the operators if necessary. You are able to put in the gain value as well as the integral value as well as the derivative value. You can go and give it limits for the output. In my case, I've gone and limited the output to 0% as well as 100%, and you can tell it where the output signal is going to be located. So all of this is done automatically for you by just using the correct block. Now, this is something that you are not going to do, but for the sake of my demonstration, I have actually put in the ability to change the gain, to change the integral, and to change the derivative. You would go and do loop tuning, and you would set these up, and you wouldn't change it again unless there was a major change in your process, such as you change the instrument, or you change the vessel, or you go on and change the valve, or something along those lines. What you would have access to is the temperature measurement, and by the way, in this case, the actual temperature is going to be my process variable, and then the operators would adjust the set point. So I want to put that in purely for the sake of my demonstration. Right, so if the instrument value is below the set point, my controller is going to take certain actions. If the temperature was to go above the set point, the controller is going to take certain actions. Those actions are going to be dependent on the PID values, which you and I would have gone and determined as part of the loop tuning. As I say, I have given the ability that we can go and give it a bigger gain, but this would not be done online. This is purely for demonstration purposes. And what you're going to find is that with a bigger gain, the initial jump is going to have a larger step. Let's take that back to a value of 1. And likewise, the response time, if I was to go and take this up, then it does mean that when it does respond, it's going to take a longer period of time to go and eliminate the offset. You can see the graph over there at the top, as opposed to me making that even faster. And then you can see that the response rate is going to be quicker, and you're going to have the derivative values that you can put in as well. So this is all going to just show us that we can do PID control using a PLC without any problems whatsoever. As always, use what has been made available to you, and it's going to make your life a lot easier. This and many, many other topics are covered in my lectures.